will tell when it is 5 minutes.
Okay, thank you very much. So I will talk about X3872 results from Belle and Belle II. And the sequence is that first I report Belle with results about decays, the absolute branching fraction. And then when I come to the width, I will change from Belle to Belle II and finish with a search for a molecule partner. So let's start with the absolute branching fraction. So maybe you noticed when you compare the PDG 2020 to the PDG 2021 that there was actually a significant change. So before, all the branching fractions had this larger than because simply the 100% were not known. And then starting from 2021, now you have fixed values. For example, here the J-psi pi 3.8 plus minus something. And the reason why this is possible is a measurement from the B factories. So there is a particular situation. The B factories are running on the epsilon 4s. And then you're creating two B mesons almost at rest. And then what you can do is you tag one side. So then you know the absolute number of B mesons that you would have on the other side. And if you then take a decay here, like a two-body decay, so you have a recoiling kaon, so you can normalize the 100% here, and then you search for a signal in the germanium part, for example. So the tagging side here, what we usually do now these days, as many experiments, is using neural networks with more than 1,000 decays. It's still a problem because the reconstruction efficiency is very small. It's in the order of per mil. But anyway, you can try. So, and Belle did this in 2018 by plotting here the missing mass recoiling to the kaon, the charged kaon. And you see the signals here for the J-psi and the eta C control signals. For the X3872, unfortunately, it was only possible to measure an upper limit of 2.6 times 10 to the minus 4. However, Babar was, with a little bit different approach, plotting the kaon momentum instead, was able to do a measurement. So of 2.1 plus minus 0.7 10 to the minus 4. And that's the 100% that you can scale all the other decays to. And the error is still quite large, 0.7, but Belle II certainly will be able to improve that quite significantly. So now I move to decays, and now I will use always this absolute branching fraction. So I will quote product branching fractions. The first term is always this absolute value of the B decays times then the branching fraction of the X decay to something. And I will start with decays to the chi sub C1. Here we had two searches. One is the chi sub C1 pi pi, and one the chi sub C1 pi 0. And both we were only able to determine upper limits of 0.6% of all the X 3872 produced, according to this absolute branching fraction. And for the pi 0 here, 3.2%. And that decay actually was then observed by Belle III, quite close to our upper limit, 3.2% here, 3.4%. Just as a reminder, that's another one of these isospin violating decays, very similar to the J-psi rho, which in the germanium region is much smaller, the branching fraction. So it's in the order of per mil. Searches for partner states, we had also two. I forgot to mention, these are always here. The 711 inverse femtobarn is always the full Belle data set that we had before switching then to Belle II. So two partner searches. One is the isospin partner or the charge partner with a charged rho. And the second one is the C-odd partner in the J-psi eta, for example, which arises in some of the diquark, anti-diquark models but this morning Feng Kun called it, I think, the compass state. So that's the one from compass, but we were not able to confirm it. So, and the branching fractions here are 2.4 or 1.7% of all the x if the branching fraction of these new states would be the same as the conventional X3872. Moving to production mechanism, there's one result, interesting result. So usually we have the two-body decay, which I mentioned for the absolute branching fraction measurement, B2K and then the X. But also the B decay with an additional pion was seen, and it provides actually the same order of magnitude for the branching fraction. So essentially it doubles all the X3872 that you can observe at the B factories. And for the neutral B, this was even first observation. So there's something interesting with that. So if you plot the K pi invariant mass, then you see that there's a resonant component, so the K star, but there's a large non-resonant component. And if you compare this to charmonium, here the psi prime and the J psi and the chi sub C1, then this is much more flat. So the resonant component is much stronger in the charmonium case, which is, yeah, it's very different from the X. In 2021, we had the observation of the X in gamma gamma even, so that so the X has 1++, so according to the Landau-Yang theorem, if you had two real photons, this is forbidden. So it can only work, and that's the case here, if at least one of the two photons is virtual. And that's a very rare signal, so it's only 3 events, but essentially it's background free. So it's the background events were 0.11 events here. How can you still be sure that this is a correct measurement? And that is because you have the control signal of the psi to S, or psi prime, which also is spin 1. So it's the same argument applies of the Landau-Yang theory. So what is measured then is the partial width.
We don't hear you.
Oh. 1, 2, 1, 2.
Again?
Can you hear me?
Yeah.
Okay, then it's a bandwidth problem. Sometimes my audio stream. Sorry for that.
We can barely hear you.
I try again, Steve. Is it better
Could
now?
you please raise a bit the volume of your microphone? You are not very loud.
Let's try now. How is that? 1, 2,
Yeah,
1.
yeah.
Okay.
Wow.
Much better now.
Okay, let's try like this. So the measurement is the partial width times the branching fraction, and it's in the order of 5.5 eV. So it's very small. So compared, of course, to a total width of MeV, so it's almost a factor of 1 million. You can also compare this to best 3 measurement, but you need to take into account the vertex factor because this is EE and not gamma gamma. But it's somewhat consistent. And that's still compatible with a prediction for charmonium. Okay, the width measurement is quite old. It's from 2011. However, as a reminder, that was a 3-dimensional fit in the J psi pi pi mode. And that 3-dimensional fit provides a kinematical overconstraint to reach observables smaller than the detector resolution. Of course, everybody knows an upper limit was determined, 1.2 MeV, very close to the actually the later world average of 1.19 MeV as it is right now from the Bright-Widner fit, of course. What many people don't know actually is the fit was validated with a psi prime as the control signal. So with a factor of 4 narrower widths, and that was even able to be determined. With a systematic error of 101 keV, it was possible to measure the width of the psi prime with an offset bias value that here, a fixed value that had to be determined. But it was possible to reach the sub-MeV precision. So now I move to Belle II. And the plan here for the width measurement is a different approach. So use not the JPSI but the DD bar pi. And that decay, it was mentioned also by Thomas this morning, is only seen at the B factories so far because of the pi zero. That makes it tricky. And we would like to use this because of the very small Q value of just 7 MeV compared to the 469 MeV for JPSI pi. If you take the case of a small Q value, then the mass resolution is getting much better. So that's roughly a factor 3 here compared to the JPSI pi. So, and then if you do the Monte Carlo simulation, this is only Monte Carlo so far, okay? The width can be measured down to 280 keV with a 3 sigma significance. If we had then in 10 years the full data set of 50 inverse Autobahn. So that's the goal. As a reminder, the Flatté fit here gets this 220 keV. This is only statistics based, so the systematics still have to be evaluated. Anyway, in future option, of course, is this tempting topic that was also mentioned already this morning is, of course, a combined fit that would be possible here of a DD bar pi and the JPSI pi. But anyway, this will not be the first step for Belle II. Production mechanism. So, and this is now data. This is Belle II data. So it's a small data set, 62 inverse femtobahn. And what you see here is on the top, the psi prime. On the left in charged BDKs, on the right in neutral BDKs, and down the X3872 in charged left and neutral on the right. Although, and you can see immediately, although the efficiency is quite similar here, left and right, there's much less yield in the neutral channel. But just to mention, already by now, a factor 4 more data are on tape. So I checked this morning, and we are close to 288 inverse femtobahn. So roughly 25–30% of Belle right now. So what you see here is actually indication of the exotic nature already. So that ratio of neutral and charged B decays. So if you define it in a way that it's neutral divided by charged, then this ratio should be small if it's a molecule, because the neutral B and K contain D quarks, the charged B and K contain U quarks, and the DD bar contains U quarks. That's the simple argument. So that makes it small. Then if it's germanium hybrid or glue ball, that should be large, more something like 1. So already, let me quickly go back. In this plot, although the statistics is very limited, of course, you can see the exotic nature or the different nature compared to the psi prime as a germanium state. But to be a little bit careful here, the fit, which means the blue line, this ratio, as was known from the B factors here, this 0.5 went into the fit. Otherwise, you would not get a stable fit here. So it has to be taken with a salt of grain. So the last topic, the X4014. So that would be a partner of the X3872 at the D-star bar threshold, predicted long time ago by Turnquist. And it would be 2++, but pure, if it's germanium or tetraquark, or it could be a mixture of 0++, 1++, 2++, of course, if it's a molecule. Here's one mass prediction that we are aware of. It's by Feng Kun and Juan Nieves and collaborators, that it's 5 MeV below the threshold. And that estimate is based on heavy quark spin symmetry to the X. However, the D-wave decay to DD bar is still possible, and that means it would not be super narrow like a 1 MeV, it would more be like 10 MeV. So we did extensive Monte Carlo simulations for that, where the state decays to dd bar pi 0 pi 0. Again, that would be difficult for LHC. And even in our case, so we use 5 different decays for the D mesons. Even in our case, that's not easy because the efficiency is something like 1% for Belle and 1.5% for Belle II. You see here the improvement of Belle II compared to 15% for JPSI pi pi. So it's not an easy channel for us. Here's one example. How it would look like. This is now for 2 inverse autobahn, which we would reach according to the predictions at some point on extrapolations at some point in 2025. And this example here, we use the same branching fraction and the same width as the X in dd bar pi with 1 pi 0. To give you an impression how it would look like with the background, the generic and the combinatorial background. And then if you do all the fits, a few hundred fits, you end up with a what we call a discovery map. So here on the x-axis, it's the branching fraction varying over 1 order of magnitude, and on the y-axis, it's the simulated width. And this is for 2 inverse autobahn, so in about 3 years from now. And the color here is in a range of about 10 sigma significance.
4 minutes.
Thank you. I will finish in 2 minutes. You see here a red line, and the red line shows you where would be the branching fraction and the width of the X in the dd bar pi 0 mode. But of course, the new state could be somewhere else. I mentioned that it would be a little bit wider, and then if it goes to more wider width, then of course the significance goes down. So if it had the same parameters as the X3872, we are quite confident that we would see this state, but it could be of course different. So the conclusion, very quick, absolute branching fraction was measured with impact to all the other decays. With measurement, we are quite certain that we can reach sub-MeV sensitivity by 2, let's call them tricks, 3-dimensional fit or a small q value. But where are the partner states? That's still also, at least for us, an important topic. Thank you very much.
Thanks so much for this very nice talk, for having achieved absolute branching fraction. That is very important. Frank, do you have a question?
Yeah, thank you, Sören, for sharing your interesting plans. On your page 18, I have a question. Maybe it was just too quick for me, and probably you have taken that into account. But you making the statement here about the exotic nature, but if I see correctly now with more time, so it's a third only the peak height of the neutral bees, isn't it? And then you have another 10% less in efficiency. So is there a net effect?
You mean that the 0.5 is not really 0.5 here in the ratio?
Yeah. Or you should really use integrals?
Check it. I'm very sure that it went into the fit. I'm very sure about that. I would have to check. So
Yes, it is. It was considered.
yes, I think the point of Frank is that the I may be tricking here, that it's really not 0.5, but I would have to check. But we are really certain that it went into the fit. Otherwise, here you can barely fix the fit. I mean, it's not converging.
Sure. Yeah, sure. That is
it's consistent because you don't put only the yield, but also the efficiency. And if you do the proper ratio, I mean, it's consistent also with the previous measurement from Belle. That if you do the comparison,
I would assume you made that all correctly. It was a little bit, maybe you double check and let me know.
I'm sure, I mean, of the value.
It's an interesting point anyhow. Thank you.
Christoph.
Thanks for the nice talk. Actually, it's more a comment regarding the decay width of the spin 2 states that you had close to the end of your talk. We've looked at that D-wave decay and found that the width could be as large as 30 MeV, but at the moment, theoretically, it's very badly determined because there's an unknown counter term. So if it can be anything between the few MeV as given in the original Guo-Nieves paper, up to 30 MeV, and where it actually is certainly an interesting quantity to look for, but it could be even larger than the 10 MeV you give. And also the pole location is influenced by the same counter term, and therefore the state could well be more bound than what came out from the original Guo et al. Paper. But I will put the reference into the chat.
Okay, thanks. I can just mention, I mean, we took really care to be also sensitive to pole positions below the threshold. And that's why we are using here the DD bar pi 0 and not D star bar, because then you could, you would only check something above the threshold. And that makes it actually a bit tricky, because if we would constrain to the D star experimentally, this would be more clean. But
why can't you directly look at D0 bar? Maybe you said it.
We can, but then you are above the threshold automatically. You are not sensitive to anything below the threshold.
Sure. No, well, you are above the D star threshold. You are below the D star threshold, and that's what matters, right? So if you just look at D0 bar, you are well above the D0 bar threshold. So you should get a nice signal, but you can measure well below the D0 star bar threshold.
Okay, now I get the point. DD bar. Yeah. Okay. That we didn't really consider. I mean, DD bar as a channel itself, we didn't consider, because I was always under the impression that the one pion exchanged for that is forbidden by parity if it's a molecule.
No. See, you have a transition D star to pi D. Therefore, you can have, if you come from a D star state, you can exchange a pion on in a T channel, and on each vertex, then you have just a D star pi D vertex. And the DD bar is then automatically in the D wave in order to conserve J. But there is no problem to go directly to DD bar. The only issue one has is how large is that transition. And in the original Guo et al. Paper, the pion exchange was included perturbatively, and they get, I think, 4 MeV, if I recall correctly. We did a study using non-perturbative one pion exchange. However, there we need an additional counter term, and we can find a width up to 30 MeV, but it can be anything lower. So that's the difference. But the one pion exchange easily mediates the transition straightforwardly.
Okay. Interesting point.
Yep.
Okay, still a couple of questions quickly. Raquel?
Yes, I just have a comment. I just wanted to say that Eulogia and me, we have a work where this spin partner of the X3872 is more bound. And this is because we don't have only the light vector meson exchange, but we allow also the heavy vector meson exchange. So this state becomes around 3,950 MeV.
So much, really. So 60 MeV bound. Interesting. Okay.
Feng Kuo, please.
Hi, thank you. Thanks for the nice talk. Actually, also regarding to the state, I think you saw a signal in gamma clearance, right?
In the DD bar.
In DD bar, yes, that's the mode that Christoph was seeing. DD bar in DD bar final state.
Yeah, that's true, but that's the chi subs. How's it called in the PDG? Chi sub C2. These days.
No, it's not that one. So there are also a signal around this mass. But with low statistics, lower than 3 sigma in gamma 2 DD bar around this mass, and around this also the width is around 10 MeV.
Okay, that I would really have to check.
The mass is below D star.
Yeah, that's below the steady star. Yes.
Okay. Okay. If Steve remembers, I would really have to check.
Okay, so
Okay. Then
there is
can-
Akim as a last question. Please go ahead.
Yeah, thank you. I have a very quick question, which is probably more to theoreticians, about this gamma production, which you mentioned on page 12. So at Belle II, one might have more statistics. And as you correctly pointed out, essentially what you measure is the transition form factor due to the Landau-Yang theory. Now the question is, I mean, do we learn anything about the intrinsic nature from this measurement? I would assume so.
I don't know. I could speculate now that it's somehow related to the annihilation part of the wave function. How the wave function looks.
I don't think any theorist has thought about this one.
Maybe some theorist wants to comment on this, in fact.
Yes, I'm sure this is indeed sensitive, because this is actually an observable that is directly sensitive to the DD star cut in the X wave function. Therefore, this indeed is an observable that's sensitive to the long range part of the wave function, and accordingly, it is really an observable that is sensitive to the molecular nature.
Mm.
Therefore, mapping out the Q-square dependence would be very valuable, because it's exactly the radius term that is relevant here.
Yeah,
as in the deuteron electromagnetic form factor, which directly sees the, if you wonder what's going into the camera, that's a cat who just visits me. As the deuteron electromagnetic form factor is sensitive to deuteron binding energy in leading order, in addition to the nucleon form factor that enters, this thing here will be directly sensitive to the binding energy and show also the significance of the cut in the wave function.
So it's an interesting analysis for Belle II.
That's right. Mm-hmm.
Thank you.
Yes, sorry, I just want to apologize that the channel that I just checked is not gamma gamma to DD1. I'm sorry about that. That's gamma gamma to gamma psi prime.
Ah, okay. Thank you. Okay. Then, yeah. Thanks.
Just a quick last comment about this analysis in gamma gamma. This is quite recent. This is the typical analysis that needs to be repeated with much more data, and there is already the plan in Belle II to repeat it. There are also plans in this moment to combine the Belle and Belle II data set. So since Belle II already reached half of the total Babar luminosity, can give some more input, but indeed we need a lot of data to repeat this analysis. So it will not happen this year or the next year. Here we have just one hint, and it's in any case very interesting. That's all.
Okay, so thanks again for the nice talk, and let's go to the next talk, the last talk of this session. So Frank, you should